So I want to talk a little bit about some of the basic concepts of probability. Now, a probability is the likelihood that an outcome will occur, and it's often expressed as values between 0 and 1, if we're talking about decimal formats, or in percentages, 0 to 100%, or in fractions. And when we're dealing with probabilities, we're dealing with an experiment. An experiment is just a process that results to an outcome. An experiment could be something like a researcher trying to figure out consumers' perception on some sort of beverage, whether they like it or not, or they want to get an idea of who they're going to be voting for in the next election. These are all experiments. Now, an experiment has different outcomes, and an outcome represents a result that is being observed, and a sample space is the total number of outcomes that could occur in that experiment. And an event is a collection of one or more outcomes from that sample space. So if we were taking a look at an experiment where we are rolling a die, and it's a six-sided die. So a sample space for something like this would be something like one, two, three, four, five, six. Right. So we have six different types of outcomes in our sample space in this experiment that we're trying to conduct, which we haven't discussed what we're going to do yet. But let's say we're going to roll this die and we're interested in the number three. Each of these outcomes in the sample space have an equal chance of it being face up in our experiment. So because we have a total of six and we want to compute the probability for each one of them, we know it's going to be 1 over 6. So they all have about a 16.7% chance of being selected or it being face up. Now, in this experiment, we're dealing with a die. The outcome listed here, the sample space is an exhaustive list of all the outcomes. And the event is what we're interested in and what are we trying to observe. So if we're saying we are interested in the probability of selecting a three or rolling a three, which happens to be about 16.7%. Right. So hopefully that gives you some perspective of what we mean by experiment, outcome, sample space, and event. So down below, I have another example, but now we're dealing with a paradise. And if I'm trying to figure out what my sample space would be in a experiment like this, I would have to jot all possible outcomes and then from there tally up my results. So if I am dealing with an experiment and I'm interested in landing a even number, let's say that would be the event that we're interested in. After I figure out what my sample space is, and I did this ahead of time and I found out there's going to be 36 possible outcomes, I could create a frequency distribution table off of this. Now, I know one of my outcomes when I roll the dice would be two. And this could only happen once because each one of the die would have a one face up. Now, when it comes down to rolling the number three, it could happen a couple of different ways, right? And I have them listed right here. I have them all listed. I'm going to unhide, go ahead and unhide this and show you what a frequency distribution table would look like based off of this sample space that I generated earlier. Here we have all the different frequencies of that outcome. If this is the event that I'm focusing on, I can look at outcomes that have even numbers and I would get their percent for each one of these outcomes. So if I were to do that, I can say relative frequency and I'll select 1 over 36. If I were to sum up this value, this value, this, this, and this together, I would get the probability of me landing an even number. So let me go ahead and do that. So if I were to select the sum of this value, close parentheses, hit enter, I get 50%. So I'm going to be talking about a few probability rules. And I have two different examples. One is related to the classical probability approach, which is the dice example. And another one is related to the empirical probability approach, where we're dealing with a data set that's related to computer repair times. And I created a frequency distribution off of this. Now, going into this classical probability approach, what we have is a frequency distribution table. On the left-hand side represents the different possible outcomes in our experiment. Now let's assume our experiment has to deal with rolling a pair of dice, and when we sum them up together, we get a result. We get some sort of outcome. So I have all of the different outcomes listed here, as well as the frequency of those outcomes based off of the sample space that I have here. So I went ahead and jotted down every single possible outcome, which makes up my sample space. So in total, we have 13 possible outcomes. So if we were trying to calculate some sort of probability event, then we would be able to get our answer based off of the information that we have here. So let's say, for example, the first type of event that we're interested in our experiment is the probability that the sum of the dice equals 2 if we were to roll the dice. So we could go to the outcome of x equals 2. So here's the outcome. Here's the value of 2, outcome 2. And based off of the frequency, it could happen 1 over 36. So this would be the probability that we would say if we were trying to look for the outcome of the sum of 2. Now for the next one, where it says the probability of x equals 7, same thing. So we can just go look at the outcome of 7. It could happen 6 different ways. That's why we have a frequency of 6. So in this case, it would be 6 over 36, and that would give me my probability. So I could, right next to these events, get the decimal version of the probability. Let's see, 2, outcome 2 over 36. And this one is outcome of the sum of 7 over 36, and so on. I can go ahead and format these into percentages, and I'll do 2 decimal. Now here's a different event that doesn't contain an equal sign. So we're saying, what is the probability if we roll the dice and we get a result that is 5 or less when we sum up those values? Or better yet, it's not 5 or less, it's less than 5. So that means we're interested in outcome of a 4, 3, or a 2. So we would get the frequencies here, sum them up, divide them by 36, and that would get the result that we're interested in. So I'll say sum of these divided by, or let me close the parentheses, divided by 36, and I get this probability. Now here we have the probability of us landing a total of 7 or a total of 11. So this one requires us to focus on outcome 7 and outcome 11. So we would get the probability here, and we would get the probability here, and we would sum them up together. And that would get our probability for the event of us landing a total of 7 or 11 as we roll that pair of dice. Let's see if I can put this all in one cell and not mess it up. So I'll say for the event of 7, we have a 6 over 36. So I'll say 6 over 36 plus open parentheses, and 11, we have 2 over 36, close parentheses, and this is what we end up getting here. Going into the rules for a second. So rule number 1 says the probability of any event is a sum of the probabilities of the outcomes that comprise that event. And that's exactly what we're doing when we're trying to solve for these events that I'm showing you over here. We're focusing on that event. We can focus on x is less than 5, which is, in our case, 2, 3, and 4. So we're focusing on that particular set of outcomes for that event. And we're summing them up together, and that would be the probability for the event of x is less than 5. So rule number 2 says the probability of the complement of any event A is P of A superscript C equals 1 minus P of A. And this is a shortcut method of trying to look for probabilities. And the best way to demonstrate this is through this example that I have here. So if we assign outcome 7 or 11, so the probability of us landing a 7 or 11, and this is considered to be an event, but we're giving this event a label and we're calling it A. And let's say there's another event where we're trying to look for the probability of it not being A. It would be notated like this, PA, and then we have it to the power of C. So this means the probability of it not being A, and if A is 7 or 11, then what we could do is look for the outcomes 7 or 11 and subtract it from 1, and that would give us a probability of it not being A. So we did compute this already here in this example. So if I want to get this type of events where we're not interested in 7 or 11, we're interested in anything but 7 or 11. So I can say 1 minus, I know that's the probability, and that would give me the probability of P of A to the power of C. This is the complement of event A. Now remember, this is a shortcut method. If I didn't want to use the complement, I could go back to my frequency table and look at each of the outcomes and get their probabilities, but I won't focus my attention on 7 or 11. And once I sum up each one of these probabilities, then I would get that result. Rule number 3, where it's saying if events A and B are mutually exclusive, then P of A or B equals P of A plus P of B. So we're looking at two events in this case. Now, what do we mean by mutually exclusive? So when it comes down to rule number 3, an example of this could be these first two events that I have highlighted in blue. So we have an event of x equals 2 and another event of x equals 7. Now, when I'm rolling the die, I know that my outcome that I'm looking for, it cannot be both 2 and 7. It has to be 2 or 7. And that's what we mean by mutually exclusive is when you have two events in your experiment and they cannot occur at the same time. So when I roll the dice, it's only going to be 2 or it's going to be 7 if these are the events that I'm looking for, but it's not going to be both. So when you have this type of scenario where you're looking at events that are mutually exclusive, then you know that you would have to add those two events up to get that probability. So it's very similar to what we have here when we're getting the probability of 7 and the probability of 11 and summing them up together. Now the keywords are going to matter. The keyword or is very important because it's letting you know that it's looking for this outcome or that outcome, not both, not 7 and 11, only one of them. So hopefully you have a better understanding of what these three rules are talking about. Now let me just go over to my next worksheet that I have. And this is a frequency distribution that I created. And along with it, I have a relative frequency and a cumulative relative frequency. And this is another way where you could determine probabilities based off of empirical data. And what we mean by that is as we're recording data, we get more information. We're better able to get an idea of the chances of something happening. Now, looking at this frequency distribution table, we could say that the probability of a computer being repaired in as little as 4 days is 0. Because you notice here, this is the probabilities that we were able to calculate. These percentages represent probabilities. If we're trying to examine the probability of a computer being repaired in exactly 10 days, then we can focus on the outcome that we have in our frequency distribution. This is not formatted to percentages, but I could go ahead and format that. That will give us 7.6% probability. So this is an empirical probability approach. So I'm going to be talking about rule number 4 in regards to the probability rules. And it says here that if two events A and B are not mutually exclusive, then this would be the formula. So we have P, A or B equals P of A plus P of B minus P of A and B. So we're looking at two events in this example. And event A represents the numbers 2, 3, and 12. Event B represents any number as long as it's even. And because we have an overlap between these two events, this would make it not mutually exclusive. And this would be the formula that we would have to use to figure out what the probability would be if we were to have either event A or event B. So the steps that you would have to take here would be first get the probabilities for event A, and that would represent the P of A. So to get the P of A, let me go ahead and type this in. That would represent the values of 2, 3, and 12. Now we're focusing on the outcome 2, 3, and 12 in these event labels, but we want to get the probabilities for each of these outcomes, which I have here in terms of the relative frequency. So I'll go ahead and do a sum of all of those that relate to event A. So this one, and this one. So I'm going to sum that up, and the probability of A would represent about 11%. Let me go ahead and get the probability of B. So all of the even number outcomes, that's it, enter, and I get 50%. Now, the third part of the equation is saying minus P of A and B. Now, this P of A and B are those that overlap. So that would be the numbers 2 and 12. So let me go ahead and say PA and B. I'm going to hit the equal sign and select the values. Well, let me do sum 2 and 12. And that would be the probability for P and A. So now that I have the probabilities for each one of these events, what I need to do is apply this formula. So I will say probability of A plus the probability of B minus the probability of A and B gives me 55.6%. I can format this into percentages. Remember, probabilities can be shown in decimal format, percentages, or in fractions. Now, remember, this is going to be the formula that you would want to use if you are dealing with multiple events, and then some of these events overlap. They're occurring at the same time. So you have to account for that by subtracting it by P of A and B. This is different from the probability of mutually exclusive events where there is no subtraction here. So just a quick recap on rule number 3, where it says if events A and B are mutually exclusive, then A or B equals A plus B. So, and we would have to kind of change the example around and say something like if event A, and we'll say is outcome 2, 4. Let me just correct that. And event B, 7, 8. Notice these events, the outcomes in these events do not overlap. So these would be mutually exclusive, and you can apply this formula here. So all I would need to do is look for the probabilities for 2, 4, sum them together, and that would be the probability for event A. And I do the same thing for event B, then I get the sum of them all together, and that would give me my probability. So let's go ahead and do that. So I'll do a sum here and focus on event A, which I have here is 2 and 4. So I'll select that and add it to that probability. Then I'll do it again to focus on event B. So this would be 7 and 8, sum them up together. So these are they're what we call simple probabilities. It's just for the events themselves. Let me go ahead and add those up together. And now I have the probability of A or B. They're mutually exclusive, and the probability would be about 41.7% of landing these type of outcomes. So I'm going to be focusing on rule number 5, and it says here that if event A is comprised of outcomes A sub 1, A sub 2, etc., and event B is comprised of outcomes B sub 1, B sub 2, etc., then this will occur. And here, what we're looking at is, if you notice between the events, we have A in the keyword and B. So we're dealing with events where they can occur at the same time. There's this intersection. And when we have this, we call this a joint probability. So I'm going to demonstrate this using a data set related to energy drink survey, where we've collected data on gender and brand preference. So I'm going to construct a pivot table off of this. And I'm going to put gender in rows, brand preference in columns. I'll put respondent in values and I don't want it to sum. I want it to do a count. And we have an idea of how female scored certain brands and how male scored certain brands. Now, let me bring over the formula or the equation related to this rule. And let's say, for example, we want to assess the probability of how females rated brand number two. So we're dealing with two events and two variables. So one is related to the gender and the other one is related to the brand. And we're focusing on females in brand number two. We have six would be that intersection that we're talking about for trying to find the joint probability between female and how they rated brand number two. So six of them out of this sample, which ends up being a sample size of 100. So if I want to get the probability of that, then I would say 6/100, and that would give me my probability, right? So that's what we are dealing with when we have events where they're joined, they're overlap, they intersect together, and you're trying to figure out the probability of that. Let me go ahead and copy this pivot table right underneath, and I'm going to change how it looks like by selecting show values as. And I'm right clicking on any of the frequencies within that contingency table. I'm going to select percent of the grand total. So the grand total we have here is 100. And this is how we'll get the joint probabilities for everything. So here I'll select that. And now I have the joint probabilities for each one of the intersections of my two variables that I'm dealing with here. So the probability of female and them selecting brand number two as their preference is 6%. And that's what we found when we were doing this manually by dividing 6/100. Now, the pivot table allows us to do some conditional probabilities. So let's say, for example, we have this type of problem. The way you can say this here is given that we are focusing on male, what is the probability that their preference is brand one? So we're kind of narrowing down who we're trying to look at in this contingency table. And one way you can do this, since we are focusing on the male information or just gender, instead of getting my percentages based off of the grand total, I would want to get my percentages off the rows since gender is on the rows component in our pivot table. So I'm going to right click, go to show values as, and select percent of row total. And now I have information that is based off of given gender. So we're saying that 39.68% of males prefer brand one in the taste test. But if we were trying to do this manually based off of this formula, what we would do is we would look for the intersect of brand one and male in the frequency table. So that would be this value we have here. Let me highlight that in yellow. So that's that intersection of B1 and male. And then the probability of male. So we're just looking at the marginal probability of male. So we're focusing on the grand total portion here on the row. That is 63/100. So the numerator part that I have highlighted is 25/100. And then the denominator, which is that marginal probability, is 63/100. So when we divide that based off of this formula, we end up getting 25, we do this, 63, 39.6%, which is the same value that I have here on my pivot table when I change the value as show row or show values as row total, right? So very handy, very quick in trying to get some conditional probabilities as well.